Welcome, everybody. Let me start with wishing you all the best for the new year, for 2022. It's great to have, again, a big audience. So this is the second series on engineering digital twins, the online seminar series. I'm Mark van der Brand. I'm chairing today. Today we start with Andreas Wortmann, and the next in 2 weeks from now, Peter Gorman-Larsen will give a presentation, followed by Patrick Desbois, Bayu Yawarandahana, and we end in the beginning of March again with a panel discussion like we did also in the previous series. So it's a great pleasure to introduce Andreas Wortmann. He's working at Stuttgart University. He's a full professor on in the domain of mechanical engineering, but as a computer scientist. So he managed to infiltrate the mechanical engineering department there, and I think he's doing an excellent job. And he's also working extensively on digital twins. Andreas has worked previously in Aachen, and from that period I know him very well. We had quite some interesting discussions on various topics, amongst others domain-specific languages and modeling. And given his move to Stuttgart, I think he also switched the topic, and I'm looking forward to what Andreas has to tell today in his, as he just announced, his provocative talk.
So, thank you very much, Mark, for the introduction. Let me share my presentation with you. Here we go. You should be able to see the non-presenter mode. I hope so.
Yes.
Excellent. So, yeah, thanks again for the introduction. The goal of this talk is a bit to provoke and to maybe shake what we believe to know about digital twins. That being said, Mark already introduced that I'm a computer scientist. I have a background in model-driven development, software language engineering, and digital transformation. I have worked in Aachen, in Gothenburg, for a short time in France, and now I'm in Stuttgart and try to, well, infiltrate production engineering with model-driven ideas and software languages. In that role, I am working on a couple of projects related to digital twins. So my insights and ideas are mostly related to these projects to some degree. And the project that has shaped my idea of digital twins most profoundly is the Internet of Production. I will come back to that later. Essentially, it's a huge research project of 34 institutes at RWTH Aachen, all across the board related to production. And we had year-long fights about a definition of digital twins, which I will present to you later. Everything you see today is through the lens of my personal, well, research background. So software languages, software architecture modeling, functional and semantically grounded architecture modeling, as well as methodical model-driven operations using digital twins. As you can see from this slide, my focus on digital twins is a bit on the operations. And in the third part of today's presentation, I will show to you a model-driven method how to create digital twins for the purpose of optimizing the behavior of a cyber-physical system. Before that, I will shortly debate famous definitions with you and hope that you jump into a debate. I will discuss properties of digital twins that we have learned from a larger literature study where we looked at roughly 1,500 papers on digital twins across all disciplines, so automation engineering, manufacturing, computer science, medicine, construction, agriculture, and whatever. Then I will show you this model-driven development, and then I would like to discuss selected challenges on digital twin engineering with you. So let's start off with a simple sentence. A simple truth, so to say, about digital twins. A digital twin represents a system. Can you, by showing your hands using this Zoom mechanism to raise your hand, can you show me whether you like the sentence, whether you think you believe it's true? No signs of hands anywhere, so the sentence must be bad.
Andreas, now you're muted.
Thank you for the hint. I'm still learning this video conferencing thing, you know. So we all, I think, can get behind that sentence to some degree. But as Jean-Michel and Steffen wrote, yeah, it's mostly incomplete. And that's something that I want to trigger and stimulate today. Because if you say a digital twin represents a system, there's a huge number of assumptions behind that are most of the time implicit. They are not exchanged, and they are not well defined. I just jotted down a few of them. So for instance, if you think about building a digital system of a cyber-physical, that is a real-world system that operates continuously, there will be abstraction. So digitalization entails abstraction. And we need to think about how much we want to be able to abstract, or how much abstraction we want to allow to call the system that we look at still a digital twin. On the other hand, we don't know what it means to be a twin. The term twin is not defined for software systems yet. When it comes to representation, and I think that's where the comments from Jean-Michel and Steffen came from, representing isn't everything. If we just wanted to have a representation, we could have a nice drawing. You know, fancy drawing with PowerPoint could be something that represents a system. Let's say a drawing of a car would work, would fulfill the sentence. There's no reason to do research on that anymore. We know how drawings work. We don't know whether when we say a system, what we mean. Is it always a cyber-physical system? Can it be a process? Can it be even a person? In medicine, we have read a couple of papers where they have digital twins of people or of organs, so of a heart, of a liver, etc. And all of that needs to be considered if you want to have a well-established foundation for digital twins that you can talk about with experts from different domains. To give you a short insight about digital twins in various domains. On this slide, you see 7 different ideas of digital twins. Yes, Mark, thank you for the comment. A human system is also a human body is also a system. I tend to agree, but if we include that, that makes subsequent definitions more challenging. And I will come back to that when we discuss the definition of Kritzinger. So what do you see here? Number 1, these are all pictures from this literature survey. And number 1 essentially is the digital twin of a chassis of a car. It's used at design time, and the chassis itself doesn't need to exist yet. So this is a kind of digital twin used in a passive fashion, which means it does not influence the cyber-physical counterpart directly, and it's used at design time, which is a complete different thing than the digital twin of number 2, where the authors described a digital twin of a truck based on diagnosis and test data. So the real thing needs to exist already. We need to have the truck we connect our digital twin to. And here the digital twin could also send data back to the truck to change its parameters. So it's active in the sense that it can change the original, and it is used at runtime. On a side note, I will try to use the term original system from now on as the twin system. So it can be an original, which means a person, a process, or a cyber-physical system. I will later debate why it cannot be a physical system. And as number 3 here, you see a digital twin of a soccer player. So we have a digital twin of a person. It's used at, of course, at runtime of the system, right? Because we cannot use it at design time, at birth of the soccer player. Doesn't make sense. And here at runtime, we connect data, we pipe it to a cloud, and we do the things that Azure and AWS and all the other things do, which means we collect data and represent them somehow. But there's no back channel to the system. So it's still on the passive dimension. Here, number 5, we have a digital twin of the probability that you get neck problems. Essentially, they take vibration measurements at your head and then project whether you will get a certain kind of neck problem. And this is called a digital twin as well, one of the examples in medicine. Again, the digital twin itself, so the digital model that we have here with the data and connectors, etc., cannot directly influence the physical original. The doctor cannot push on a button, say, yes, now your neck is okay, and suddenly the patient's neck is okay. Doesn't work. In number 6, we have the digital twin of, how do you call them? These rotor wind turbine. Yes. And this is a kind of digital twin that I like very much because, and I'm taking, so essentially the digital twin here is a software system. It's a complex system featuring connections, databases, models to control the behavior of the wind turbine, to optimize the behavior. And we will later see that I think that only this and possibly this with a truck are useful digital twins. But again, we can debate that. Steffen, there was a comment, not yet. What do you mean?
Sorry, I was being facetious about your feedback on the feedback loop on the human neck.
Ah, okay, yes. Maybe that might become a digital twin in the future, indeed. So we have seen digital twins in literature all over the place. And I will show you why this is a bad thing. Essentially, I want to be able to talk with you guys or other researchers, and I want other researchers to be talk among each other. And when they say digital twins, they have at least a very, very good and commonly shared idea of what they talk about. Do they talk about a CAD model of a chassis, the passive design time twin, or do they talk about a complex software system of a wind turbine that actually manipulates the original system? And we have looked at definitions in literature. I told you 143. And there are 3 main classes of definitions I have found, or we have found. 1, ambiguous ones. Digital twin is a digital avatar. Cool. We have no idea what a digital avatar is, but yes, you can call it that. It doesn't help. Same if you say it's a replica of a business process. What is a replica of a process? What does it mean? What is a mimic of a real-world asset? Or is a digital duplicate? So without defining these terms, these definitions are pointless. The second category are very narrow definitions, where essentially you focus on a specific kind of system or implementation technology. Say, okay, you know, a digital twin is a digital model of a real network environment. If you write it down like that, it says all digital twins are models of a real network environment. And I don't want that. And that doesn't make sense, because then we cannot have a patient digital twin. Similarly, we can focus, we have found definitions focusing on products, on specific technologies. And I think that doesn't make much sense. I mean, we also don't say, yeah, a model is something that can be generated to Java. And then there are definitions which are essentially unfeasible. So theoretically, that sounds nice. Practically, it's hard to do that. So an integrated virtual model of a real-world system, and now comes the problematic part from my side, containing all of its physical information. So I brought this example on earlier. Most of you, or some of you know that maybe. If you work with large bodies of fluid, for instance, even the moon might have an effect, and then a small effect on how this large body of fluids behaves. Most of the time, you don't want to move, you don't want to integrate celestial bodies into your manufacturing models. Similarly, if you really want to contain all of its physical information, you need to go down to the level of the individual atoms. And also that most of the time doesn't make much sense. Because either we can't do it or we don't need it for a model to be precise enough. And then there are definitions that are just bogus, a complete something. We don't know what complete means in the sense. If it would be complete, it would be the original thing. So that doesn't help. But there's hope. There is a direction in defining digital twins as a model that focuses on simulation and requires an existing system. There are a lot of these definitions. So for instance, a digital twin is a software model that has mechanical, electrical, and physical data. And it uses holistic simulations and describes existing manufacturing cells. So, by sign of hands, how happy are you with this notion of digital twins as a simulation model of an existing system? Okay, so at least Mark is happy. Jacques is asking why simulation. Daniel doesn't like it. Yeah, let's use all the options of Zoom that we have to communicate. Happier, but where's the feedback? And does it always have to be simulation? Yes, actually, if it was that easy, I would say, well, thank you for attending my talk. Have a nice evening. But then we would need new terminology. We would call it a simulation model at runtime, and we would be done with it, right? And we know how simulation at runtime works. There's a lot of research on that. So I would say if we want to actually consider research on digital twins, we need to do something more. As Andre just wrote, simulation is only part of it. This is something I can get behind, because let's have a look at a couple of examples. We see a couple of models, and all of these here can be used for simulation to some degree, right? We could use a CAD model, circuit diagrams, state machines, and math, of course, to simulate the behavior of a system to some degree. But these models, again, aside from models that bring their own interpreter baked into the abstract syntax tree, do nothing on their own. They need structure, infrastructure to be interpreted. They need a simulator, transformations. They need connections to data sources, and so forth. So a digital twin cannot be a model, cannot be only a model. A digital twin needs more to do something with these models. And as raised by the comments, it will most likely not only focus on simulation. Another thing that was not debated yet, and I'm wondering why, is that the digital twin needs to focus on an existing system. So I might suggest the following improvement. A digital twin is a software or software system comprising models and services to use these models. Again, I'm biased. I conduct research in model-driven development, so that might be debatable. But this does not prescribe that we need to focus on an existing system. We don't need to focus on simulation. And it's not a model. It's a complex system, maybe multiple models, maybe heterogeneously models, multi-level modeling, whatever we have, to describe, at least describe and represent cyber-physical original. And of course, this is not my idea. There's a lot of research on that, and there are a couple of definitions that are quite good, I think. So for instance, Mark, this definition I learned through you. There's a question by Steffen, but a twin of what? Yes, that's a good point. Here I just wrote nothing, and I would say of a system. This is missing. And by a software, I mean it's software. And it could be an information system that uses models. It could be a kind of a fancy IoT dashboard that allows us to automatically do some AI techniques, to leverage AI techniques to change the behavior of the system. But the point I want to make is it's software, it's digital. And I will come back to that. It also needs to be connected to runtime data of the system. Yes, excellent. You're taking into consideration everything I want to bring on through this talk, but this is due to Mark and Francis and me often talking about digital twins. So thanks for your feedback. Mark, this model I learned through you. There's the, by Key et al., the 5D digital twin model. And they came up with the idea that the digital twin has services that are connected to virtual models, that are connected to data, and connected to physical entities. So this model has everything that we just debated, right? There's a connection to data, and everything is connected to data. There are kind of models for different purposes, and it's not prescribed for which purposes. Could be design time, could be runtime. But in this model, this here in the blue box is a digital twin. That means the digital twin cannot easily exist without the physical counterpart. So if you wanted to use this kind of digital twin at design time to do, for instance, design space exploration, that wouldn't work, at least according to this definition. Moreover, another challenge in here is that the physical entities cannot be purely, and that's the point, purely physical. Because if they are purely physical, how do you connect these to data? Let's say, you have a cinema chair, stupid old cinema chair. And now you have a service, you can book this chair in the cinema, and you have some data, just a Boolean, it can be booked or not. And you have a virtual model, let's say a CAD model, showing some details about your chair. How would this physical chair provide data? Exactly. So either this needs to be a cyber-physical system that has connections to talk about its status, to accept messages, to react to services, or in this definition, a lot is hidden into the connections. So in here, in this connection between data and the physical cinema chair, there could be a webcam doing object recognition to check whether the chair is used or not. But if that would be the case, then I think this definition is a bit challenging because it's hiding a lot. Also, whether processes can be twinned in this definition is debatable. So apparently it says physical entities, the process by itself is not physical. You can, of course, debate whether you can observe real-world processes without observing the systems that observe the process. So whether you observe a process and have a process twin through a twin of the cyber-physical sensors that you're using. But that's not debated here right now. Another, even more popular definition by Ceci et al. Works on data flows. So here, in this characterization, essentially, depending on the data flows that are used, one distinguishes whether it's a digital twin, a digital model, or a digital shadow. And if you have manual data flows between your physical object and the digital object, yes, there's a comment by Mark, the physical system has to be defined. Can you elaborate on that? You mean in terms of software or in general in the definition?
In general, as definition. Mm-hmm. Because you take the example of a cinema chair, but the question is that the example that you should take?
I tend to agree. I could have used the patient as well.
Yeah, okay, you could have taken a spoon or whatever. So I think the point is that the system in a way should produce data and should work with data, and otherwise it is, and data can be in that sense very broad, but otherwise if it's a system that is just there without any intelligence, then I would say it doesn't make that much sense. But that's
I tend to agree actually. In the literature study we have seen a digital twin of a block of metal. So people had a block of metal and they observed that via camera and scales and whatever, and they build up what they call a digital twin. And I would highly debate that this is useful, nor that this is a digital twin, because there's no feedback loop. So yeah, but we need to work on that as a community. In this model, if we have a physical object, again, let's call it physical object for now, and a digital object, the data flows are manually. So in this example below, if I have a real car and a CAD model of that car, and I change the color in the cut model, then I change the color in the real car and vice versa. But I do that manually. So I make my cut model green, someone needs to go to the car, paint it green. If someone paints the car blue, someone needs to update the cut model to make it blue. Funny thing is here, in this definition, it's not clearly defined what these data flows mean, actually. And what you can see from this example already, they are not equal. If I change the real car, changing the cut model is fairly easy, so the color, right? If I change the color in the cut model, changing the real car might be much, much more complicated endeavor. I need to get hold of the car, I need to tow it to a place where it can be, the color can be changed, people need to change the color, etc., etc. So these are not equal, and I'm pretty sure that the future will show that not everything here that's possible on one direction is possible on the other direction. So these are also not symmetric. If we then have a digital shadow, we got a first automated data flow. Here, there's an automated one-way data flow from the physical object to the digital object. And its change in the state of the physical object then leads to a change in the digital object, but not vice versa. Again, back to the example, we have a real car, and in our car we have a dashboard, and here the small red box you see, that's actually a top-down view of the car. If you open a door in your car, this digital shadow of your car is updated. So the representation automatically shows you that the car's door now is open. And again, the data flow in the other direction does not work automatically. So even if you could close the door on this dashboard, it would not close the door on the car. And why is it called a digital shadow? Because the representation of the physical object is following the physical object by this automated data flow. And now we can drive this analogy a bit further, which I think is very important. A shadow works on a specific illumination, so for a specific purpose. I have a light source, I cast it on my object, and I get a specific shadow. And similarly, I have a specific purpose, a specific intention that I want to look at in my regarding my physical object, such as the car doors being open. And for that, I might have a specific digital shadow. So maybe I have a maintenance shadow, I have an insurance shadow, I can have multiple shadows of my car for different purposes, for different stakeholders at different levels of completion, complexity, abstraction, and granularity. And for a digital twin, things change. Now suddenly, we have an automated data flow back. So the physical object changes, the digital object changes. If the digital object changes, the physical object changes. And while the digital object in the digital shadow can be a stupid data structure in a database, right? Just a table, car door status for Booleans, easily done. Here, for the digital twin, so the digital object in the digital twin, we need more. We need some way to send back data to the physical object. And now, if the digital twin can send back data to the physical object, it would be boring if the digital twin would ignore that data, right? So it needs to do something with it. Otherwise, that's pointless. And essentially, there are two things it can do. It can configure the physical object, or it can directly control the physical object. In both ways, if it doesn't change anything in the physical object, sending data is pointless. We could just stop it, right? We don't want to use a real car as a virtual hard drive, where we just pump data into to have the data stored in the car. So suddenly, the digital object needs to have data connections. It needs to be able to store data, to react possibly on changes in the physical object. But again, if that object is purely physical, the cinema chair, that doesn't work. Unless, again, in here we have a webcam, AI, or any kind of sensors. Important point, a digital object must have actuators that allow us, so software actuators at least, to change the physical object, and software sensors to react on changes in the physical object. Yeah, they're good comments. So digital twins have a purpose. I will come back to that later because I think the purpose design defines the shape of the digital twin. So depending on the purpose, you might have multiple digital twins of the same system. Maybe your insurance company has one for your car, right? Your manufacturer will have one for your car to see whether you have the latest add-ons and monthly payments for your four-wheel drive or whatever add-ons are installed. You might have one for yourself. Your garage might have one, etc. Yes, that reminds Andre to the classical mechanical closed loop of sensors. I tend to agree, but if you look at it from this perspective, everything is a classical mechanical closed loop. So I think this is a bit more complex because the decisions it can make should be more complex, but I don't debate that. There's a question whether the physical object has to be designed with a physical twin in mind. Yes, indeed. If I want my digital twin to make any decisions about, let's say, closing the doors of the car or not, then the car's API, or at least the car's interface, so whatever we connect through to the car in this example, needs to be able to have a service for that, or a function, or whatever we can call. If that's not possible, the digital twin cannot do anything. So whatever interfaces you provide to your cyber-physical objects restricts in some kind what you can do in the digital twin. Another example, the car most likely, unless it's a Tesla in this example, doesn't know its color. So the digital twin usually cannot sense the color of the car. And even if you say your digital twin has a color and you can change it here, you will not make any changes to the physical system anyway, because there's no way to change the color on the car. So there's a relation between the digital twin and the services you want to provide. Yes, exactly. And that's something that needs to be considered when you start engineering a physical object, because you will limit or enable features of your digital twin. In this definition, there are a couple of hidden problems, I would say. For instance, these data flows do not talk about liveness. So is it okay for a digital shadow if this update here from the physical object to the digital object happens once in a blue moon? Or do we have hard real-time constraints on that? Or do we just not care when we talk about digital shadows or digital twins? I already discussed the lack of, or the issue of precision. So if we go from a continuous process to a digitalized process, we might lose precision. And maybe that's okay for a process. But again, this is hidden in this data flow, and the definition doesn't talk about that. Because if we lose 100% of precision, that might become a pointless digital object. So maybe there's even a notion of fidelity in digital twins, such that a digital object can lose its status as a digital shadow or digital twin depending on the quality of this information flow, or in the case of digital twin of this as well. So if I lose means to change the physical system, can this still be a twin? There's a good question by Steffen. How does update frequency interfere with the ability to do useful things with a twin? Yes, that's a good question. And I think that highly depends on the kind of twin you want to build. But that's a question that needs to be considered when building your digital twin. So for me, this again implies a digital twin is not purely and solely a model. It's a software system that has connections to the physical object to receive data, to sense data, and to manipulate the object, and do something with models in between. Why models? Well, I believe in model-driven engineering, so there must be models in there, but it must be more than models. So that being said, we tried to work on a better definition in the Internet of Production.
Maybe Andreas Mark also asked what is the difference between the digital object and the control software. I think that's also related to the Kritzinger definition.
Yeah, that's an excellent question, and I don't have an answer for that, because even if you think about it, there's a separate thing called digital twin, and there's the controller of the software object. And the controller of the software object now is on the cyber-physical system in the car, right? And now you say, yeah, well, my digital twin, it can move from the fog to the cloud, to the edge and whatever. Can it live on the physical system? If it can live on the physical system, why isn't it integrated into the control software? And I think that's where talking about digital twins of legacy systems becomes important. Where you say, okay, I have a system that's in use, that has, for instance, hard real-time constraints. I don't want to interfere with that system because it's in use 24/7 or almost 24/7, but I want to add new expertise, new insights, new strategic information that I have on top of the system. So I don't want to change the control software because that might require certification, that might require whatever, but I want to set something with new expertise and knowledge on top of that, which I can maybe change more easily. Other than that, I like your question very much because the question, why isn't whatever you propose to be in the twin not part of the software system itself, is a good one. And I get that very often. Do you have an opinion on that?
I'm struggling with this question as well. That's why I posed it. I see that in the future, the digital twin and the control software will become one. Not now, and I agree to your observation with respect to the legacy systems, but especially if you start designing your physical object with a digital twin in mind, then this really raises the question, okay, what's the difference in the long run?
Yeah, I fully agree. And I would even say there are only a few use cases where the separation needs to be considered. So for instance, when you have the digital twin of something that's essentially an embedded system, you don't have the computational power to do, let's say, simulation at runtime on the chip itself, but you want to predict its behavior on the cloud. There was an example, I think it was proposed by you, Luke, where digital twins for soccer robots were deployed, had to be deployed on the system itself, right? So there are strong cases for both directions. Steffen, it's just models at runtime then, right? I tend to disagree. Models at runtime doesn't say anything about being connected to a cyber-physical system.
Sorry, what I mean is if you merge it into the control software, then that's pretty much where you are.
Might be, yes, indeed. I also do not want to deny that these two are very, very close. And maybe it's more on the focus of application where the digital twin really differs.
I'm being happily facetious here, by the way, right? It's sort of later in the afternoon. I mean, that's so do feel free to shut me up when I get annoying.
No, I like your comments because I get this comment also very often. Okay.
If I may add to that, Andreas and Steffen, I think that we should make a difference between we should make the difference between an engineered system and a natural system. So a natural system, a human being, Earth, whatever, something that we cannot influence, and an engineered system, something that we can influence. Francis and I had some discussions on that topic as well.
I think, Mark, if I may add, Andreas, just like to clarify, a natural system you can influence, you cannot control. It's different, right?
Yeah, that makes sense. Maybe that's a distinction that we should keep in mind. So a couple of slides ago, I was talking about active and passive digital twins, essentially, right? Maybe we need to have terminology to discuss these different kinds of twins. So a twin of a natural system that is only influencing versus a twin of an engineered system that is controlling. And maybe clarifying these different kinds of digital twins is something that we as a community need to work on. So that we don't talk about digital twins to another, but maybe Francis wants to talk about an influencing passive active digital twin, and then I better understand what he's talking about.
But is that right, that distinction, right? So if we move this forward a little bit and sort of go and say, okay, so if we think of a digital twin for the moment of a patient, right? So we can potentially collect data, say of a patient's heart, right? So we can potentially collect data of that, possibly in an automated way, even by doing sort of scans of and having sort of a pipeline, a data processing pipeline after that. We might be able to do that, and there's work that tries to do that. And then we have a digital representation of that specific heart, and we can simulate it and learn things about it and come out with maybe some sort of diagnosis about it and some proposals for what we might want to do to improve the patient's prognosis. And then that gets shown to a doctor, and the doctor sort of has a manual, and there's a manual data flow through which the doctor then controls the system effectively again, or tries to influence the system effectively again in some way, maybe through medication or through advising on change of behavior and so on and so forth. Now, I've consciously used the term control here because I think it's a similar level of control as we have over any other physical object, where what we do, what any control system does is it changes some inputs to the system in the hope that that will affect the system behavior and some sort of output parameters in a sensible way. And typically there's a feedback loop that then measures whether we've achieved that change. And if not, that sort of tries to make some changes. And how successful we are in making these changes largely depends on how well understood the physical object is, right? And the reason why it's more difficult to control humans or to control processes is perhaps more than engineered systems, is because they're perhaps less well understood and sort of more complex systems than engineered systems, where, in an engineered system we're purposefully trying to reduce complexity and reduce it to complicatedness perhaps, and purposefully try to design them in such a way that they are easier to control. But even there, right, I mean, if we think of a power plant or a pump system or something like that, even there we need a control loop, a feedback loop to control the system, because we need to measure the effect of our actuators on the system. So I'm not that that differentiation really holds up necessarily, of saying you can't control a living being, because it's just that it's more difficult because we don't fully understand it, or we understand it less well than an engineered system.
Or the control is less direct, right? I mean, it's a very good summary, Stefan. I mean, I completely agree with what you said. I'm trying to apply some of these concepts to DevOps or software processes, and that's exactly it, right? Yeah. And then the monitoring a patient is exactly right as well, because some of it, maybe there are some actions you can take that have a direct impact, like a direct almost control. Other things is just influencing, like trying to change the behavior of someone. You can bring directives. You don't know how they will be interpreted and implemented. I'll shut up here. But that was a very good summary. I think that what you said captures a lot of both the essence, but also the reflection we've been having in this group to wonder what the digital twin is. that Andreas has summarized quite well. I really like this picture, Andreas.
Yeah, thank you. There's a comment by Mark.
I have no comment. I'm interacting as a chairman, but because we are moving in a kind of panel discussion now, and I don't think that is the purpose. So I would like Andreas to continue with his presentation, and given the time, and pay attention to the time. Let's put it like that.
I will. Thank you very much. One suggestion: let's move that to a panel at the Modded workshop at Models. These discussions. Okay, so we try to work on another definition that basically builds on models, digital shadows, and services. And they must be used purposefully with respect to the original system. This is where the purpose comes in. And we try to build that on better understood foundations. We have the models in the sense of Stachowiak. We have digital shadows. There's a couple of publications on that. By the way, I will share the slides afterwards, and you get all the literature references. And it does not prescribe a purpose, so it's not for manufacturing or for automotive. It does not prescribe an implementation. You don't need to use AR if you don't want to. And it captures most of the definitions we have. But all the definitions we have seen so far do not talk about what a digital twin needs to do. And we thought about that and came up with three main purposes of digital twins, again, based on this systematic mapping study. So the main purpose essentially is presenting the original system. So without presentation, without knowing what the system is doing, you can't do anything else. And this can be through logs, databases, models, whatever you have. If we have this presentation, we can build on top a prediction layer. So we can predict how the system should or would behave. For instance, in a digital twin that checks your braking assistant, or whether the cinema chair should be used or not. This could be predicted, for instance, based on previous number of tickets sold for a specific movie. And it should be able to prescribe the behavior of a system. So that is this feedback loop from Kritzinger, where you essentially send back data from the original, from the twin to the original system. If you don't use this to change its behavior, then this feedback loop is quite pointless. And this is also what we found in literature. So essentially, you want to change the behavior. Couple of comments in the chat. Daniel, can you have a look at them and maybe say something when I need to react on something?
Yes, there is one comment from Jacques, but that also engineered systems may require manual non-automated control. But yeah, not sure how much you want to react to it given the time. That's up to you.
I think we agree on that. Now my representation broke. Okay. We also want to be able to use digital twins across a complete life cycle of the original system. There are many different purposes there. That is design space exploration, evaluation, supervision of production to find deviations from the model to the reality, tracing of materials, learning from operations, improving behavior, ultimately improve the engineering of the second version of the system. If we have the digital twins of a car, let's say the Tesla Model S I had on the slide earlier, we record its lifetime, we can use this data to, for instance, optimize the next version of the car. And essentially, that's why I think digital twins are an excellent basis for kind of a model-based DevOps, where you use digital twins at design time to build the system and at runtime to optimize the behavior of the system and go back again. And whether this is always the same digital twin on the left side and on the right side, or whether there are smart transformations translating the left side to the right side and back, I don't know yet. So coming back with another suggestion, a digital twin is a software comprising models and services to purposefully represent and manipulate its original system across its complete life cycle. I have to say I like that, but to be honest, that's kind of idealized. We are not there yet. But at least it gives us a purpose, and with the purpose, we have the opportunity to say there are multiple digital twins for a system. And we can use them at runtime, at design time, or for maintenance, insurance, whatever. And that also could liberate us from forcing the use of a single digital twin across a complete life cycle. I agree with Mark, use digital twin for optimization in a broad sense. Yes, that would be the hope. And as I said, this is kind of idealized, but I think that should be on the horizon. That's something to strive for. So this ends the part on definitions, and maybe we should plan for another slot in the series. Because we have also extensively looked at properties of digital twins. And I will just give you a teaser today. So
maybe before that, one comment from Steffen that services feel a bit general here. With the question added, is an analysis tool a service, or does it have to involve some form of feedback to be a service? It's
deliberately broad here, indeed, because there might be so many different purposes for digital twins that entail different services, as Mark raised earlier. But maybe that can be refined by discussion in this community. So we looked at a couple of papers. It's 2,400 or 2,600. And we try to find out who uses digital twins, what are their properties, how are they engineered, deployed, how do they operate, and how are they evaluated. As you can see, for instance, with respect to the purposes, what I've told you earlier, it's used for monitoring, behavior optimization, prediction, and validation. Steffen, if it's only an analysis tool, then it's only digital shadow. Yeah, most likely, because it's lacking this back channel. So if it's only analysis, it could be a dashboard, an information system. And we need to work on a better definition. I fully agree with that. And yeah, what you can see here, there's a strong focus actually on runtime in literature. There's even work on design space exploration at runtime, which I found quite strange. But there's less focus on design time digital twins. Also, we found a strong focus on manufacturing in the survey. Also, the only search term we used was digital twin. But I think other domains like agriculture, medicine, construction, especially with BIM, are following up. We conceived, we collected essentially kind of a feature model for digital twins that distinguishes features on the purpose, or aspects on the purpose, the realization, the deployment, and the operations. And I will briefly go through them due to lack of time, and then we'll see. So, for instance, when you engineer a digital twin, you need to think about how many counterparts do you want to have, and what kind of counterpart do you allow for? We just discussed that if you have a human being as a counterpart, the original system, you cannot just push a button and change its behavior. You need to debate whether you want to allow for multiple digital twins or not. You need also to identify whether you want to use the digital twin at design time or at runtime. At design time, the thing that you're twinning doesn't exist necessarily, whereas at runtime, you can work with real runtime data. And orthogonal to that, you can also think about different representation phases. So the digital twin as designed usually is a very idealized version of your system. The digital twin as manufactured will have deviations due to manufacturing. And these might impact the precision of the model and the services you get. And even later, after, in the life cycle of the system will deviate more and more from the original initial S-design model. Because, you have wear and tear, you have historical, you have a usage history, you might have updates and stuff. And suddenly you might end up with a digital twin that you want to use as design time, but you focus on the phase as operated. So at design time, you want to focus on the specific system and how it operates in the future. You have to you have to think about how you want to interact with the asset, direct or indirect, similar to the counterpart decisions. You have to decide whether you want to do optimization or not. Do you want to optimize the digital twin only, the CPS, both? And you have to think about the constituents. I will leave this online, and I think Luke will send you the link, or we put it on the website so you can browse through the other parts of this tree. What we found out is that there's again huge focus on digital twins as operated, bit on digital twins as designed, and virtually nobody cares about digital twins as manufactured. Maybe because that's a very short lifetime only from as designed to as manufactured to as operated. The thing is, even only very little research considers any of these combinations. So we will have our model as designed with our idealized assumptions, or digital twin as designed, sorry, with our idealized assumptions, and we will have our running system. The running system changes, wear and tear, history, updates, etc. And the predictive power of the digital twin will reduce due to the model not being updated automatically. So meaning it's not automatically transferred from an as-designed model to an as-operated model that grows with the system. And that is something research should take care of, definitely. So I will now skip this part and go directly to selected challenges because I have 5 to 10 minutes left, I guess. Is that correct?
No, max 5.
Okay. So yeah, this slide I want to show you because this is a problem. When we talk about digital twins, some people talk about digital twin types. So a model of a digital twin that holds for all kinds of Tesla Model S, for instance, right? That's your Model S design. This should hold for every Tesla Model S. No, I'm not sponsored by Tesla, by the way. Then you might have a digital twin instance, a specific digital twin system, model system for a specific Tesla, like the Starman Tesla that I shot to space. And then there's the digital twin implementation. So ultimately, source code plus models on a computer that do something. And when you say digital twin, maybe in the future, think about what you're meaning. Do you want to talk about this, the type, the instance, or really the implementation, the thing that ultimately runs on a computer? And I think we as researchers should make that very clear when we write publications. So I will not bother you with that and or method. That all of that can be read up into literature. Let me conclude with a couple of research challenges or questions. So I have shown you initially these definitions of digital twins, and most are either ambiguous or narrow or impossible, and most don't answer these questions. So can we have more than one digital twin for a system? Coming back to Mark's comment, what is the system boundaries of the digital twin? Why is it not baked into the software? Can we twin a physical being, or is that then a digital shadow only? Can the twin exist before the original? How do we migrate from as designed to as operated? What's the fidelity of a digital twin? And all of this needs to be answered. The problem is we don't have good definitions. So we need a good intentional definition of what a digital twin is. We don't have it. And maybe we need many for different purposes, different runtimes, different levels of interaction with the physical system. So the first challenge I want to propose today is come up with a commonly acceptable intentional definition of a digital twin that does not rely on undefined terms, does not rely on specific domain, and is actually feasible to achieve. The second challenge is actually leveraging the knowledge that we have. We build digital twins of systems. These systems, engineered systems, are built by experts. There's a huge body of expertise written down, codified, modeled, coded in building these systems. We need to be able to generally and in a systematic general fashion to leverage this model to build digital twins. Because currently most digital twins are handcrafted, they are ad hoc, and of course that does not scale up. We as software engineers know that reuse is the key to success, and that means also reusing engineering models to derive, build digital twins. Coming back again to reuse. Reuse is a key to software. Think about building the string class. Every time, again, you build something with Java. No one of us would be able to do anything else than coding basically software. We don't have a good idea how to reuse and compose digital twins at different levels. Say, for instance, you have a factory, you have a digital twin of your production device. You maybe want to have a digital twin of the factory that somehow incorporates these production devices. You maybe want to have a digital twin of your manufacturing capabilities as a company or even as a company. And all of these need to build on another. That can be loosely integrated, that can be composed to produce new, more digital twins with more information. But in this composition, in this integration, there are many challenges. Like, for instance, abstracting away from features, providing new services, etc. Mark, I'm coming to an end. And the third challenge is to enable the composition of digital twins from simpler digital twins. And now, my essentially last slide. We debated that last time. Do we want to have a Turing test for digital twins? Short answer is yes, cool, Turing test. We love that, right? Of course, the Turing test itself is debated by the Chinese room experiment, but that's not my point. My point is, if we wanted to build something like that, we would have a questionnaire that puts queries to our digital twin on the left side and to the cyber-physical system on the right side. Then, after a time, he or she must decide on whether he has talked to the digital twin or not. Problem is, again, we might have different communication channels here that have different levels of delay, of abstraction, message loss, all these things that essentially might allow a smart questionnaire to distinguish both systems, just due to the nature of this one being physical with some sensory information on top, and this one being purely software. Also, if we go for this kind of test, the digital twin of our car is not allowed to know the color of the car if the car doesn't know it as well. So we would restrict ourselves a lot in what digital twins can do. And I don't think that's the thing to have. So we might need a better notion of this test for digital twins. The summary and the most important message here. Hopefully there will be a workshop on model-driven development of digital twins at Modules 22. We will propose that again, and I hope I will see all of you back at this workshop. That being said, I am in time. Thank you very much.
Okay, Andreas, thank you for the excellent talk. I think it was very, very useful, and I learned a lot of it. And I think more people, given the applause that you got.